Thank you very much, Bryce. And just before I begin, I just want to thank you, Bryce, and Geshe Lakhdar for organizing this meeting, and to all the translators who've been extremely helpful in the past 2 weeks here. And it's been a pleasure allowing me to spend time with the Geshes and the other group of monks here in the last 2 weeks. So I truly appreciate it. As I was preparing this talk over the last couple days, I was kind of reflecting on what all the other presenters have said. And I think many of the issues that were brought up will come together because first we talked about how do we know things. Chris Empey was able to give us a history of how the Western scientific perspective came into being. And then we heard about how we extended our senses. And today what I want to talk about is actually how to act. And that is, you need to still pay attention to the science that I'll present, but I want to hopefully concentrate more on how we should respond to some of the new research. And what I'm going to do today is present some new research from various labs around the world. And I'm not going to justify the research. This is up to you to make a decision for yourself. As Geshe Lakhdar said yesterday, personal responsibility is very, very important. And some of the research that you'll see that I'll present, it might surprise you, it might shock you, it might actually bring you joy. And so I hope that you'll pay attention to the actual research, what is done, but then perhaps think to yourself, how do you respond to some of this work? It is not science fiction. This is work that's currently going on to the research labs. Many of the research that you'll see is in the very, very early stages. Other research has been turned into products that you can actually buy off the shelf. And so when you see this work, think to yourself, is this a good thing or is it a bad thing? My wife has sometimes said to me that I can argue on either side. Knowing and working with the Geshes, I'm not sure I'd want to be on the opposite side of the argument with them. But some of these questions, I think, don't have answers yet. And we need to talk about this as we move forward. So the general outline for my talk today is first talking about the difference between the ethics of neuroscience and the neuroscience for ethics. And then I'll talk about some examples of research that's being done. And then I'll talk about perhaps what should be done and your input about how you approach some of these new research findings, I think will be very interesting to hear. So first, I'm going to talk just briefly about what I'm not going to talk about, and that is the neuroscience of ethics. And that is when someone is posed with an ethical or moral dilemma, how does the brain respond? That's the neuroscience of ethics. And for example, if a train was going down a track and there were 5 people right in the face of that train, but there is a little turnoff, and you can pull a switch so that the train would not hit the 5 people and kill those 5 people, but instead you would pull a switch and it would only kill 1 person. Would you pull that switch? So some people would say, yes, I would pull that switch because I would save 5 people, but yes, it would kill the 1 person, but that's a good thing to do. Other people would say, no, that's fate. If it's going to kill the 5 people, I shouldn't intervene. Some people would say, well, would your decision change if that 1 person was your mother or father? Would you still pull the switch? How does the brain respond? Another question, or maybe it takes more people. Maybe it would take 10 people to kill that 1 person. Or what about this? The train is going down the track, and instead of pulling a switch, would you push a person in front of the train so that would stop the killing of 5 people? Would you push the person or not? These are questions that scientists have asked and have looked at how the brain makes a decision. What parts of the brain are active making a decision? So that's the neuroscience of ethics, which I'm not going to talk about. Rather, what I'm going to talk about is the ethics of neuroscience. That is, how should researchers and the public investigate issues and think about issues related to the brain? And you might be asking yourself, well, why is that important to you? Why should you be interested in how the brain works? Why should these decisions that are being thought about, why is the research in laboratories, why should that be of interest to you? Unfortunately, we'll all probably be affected either directly or indirectly by neurological disease. Neurological disease is extremely common, whether it's caused by injury or disease. And what you see here on the screen are just some examples of, this is just the total number of cases and the cost in dollars in the United States alone. And you can see that it's very, very expensive, both on an emotional level and also on a financial level, to take care of people with diseases of the nervous system. So perhaps by knowing about the possibilities of cures and treatments, you can make better decisions about people that you know and love. So I also want to concentrate on two particular disorders, stroke and Alzheimer's disease, because these are becoming more and more prevalent in the coming years. For example, stroke. Stroke is caused by the blockage of blood flow to the brain, which can cause neural tissue to die because it lacks oxygen and nutrients. It's been estimated by the year 2030 that almost 4% of the US population will have had a stroke. That's 1 in 25 people will have had a stroke. That's a huge, huge number. It's going to be very expensive to take care of these people. And again, the emotional cost to friends and family is probably immeasurable. So neurological disease, specifically stroke, will be very, very common, and we'll all probably know someone who's been affected by it. Around the world, the incidence of dementia is going to increase on almost epidemic proportions. And it's been estimated by the year 2040 that almost more than 80 million people will be affected by dementia, that is, loss of memory problems and things like that. So it's very important, I think, that each of us, even if we're not researchers, to know about these diseases and possible new technologies and treatments for people that we know. Where I am at the Center for Sensorimotor Neural Engineering in Seattle, we study neurotechnology. What we're interested in is connecting the brain to a device, mainly to help people with movement problems. So these are people, from my understanding in the last few days, these would be people suffering from that gross level of consciousness and the top level or bottom level of suffering. This is outward signs of suffering, people that can't move, people with spinal cord injuries, people with stroke, people with ALS, amyotrophic lateral sclerosis, and other problems of movement, even lost limbs. How can we help people that can't move because of disease? And we're interested in how nervous systems work. So basic science about how the brain works, how the brain processes information, how information is stored and then retrieved. We're also interested in engineering materials that can interact with the nervous system. What are new ways that you could connect and listen in on that electrical activity from the brain? What are some methods to record? How is that information analyzed? And how can we make sense of that information? And finally, we're interested in engineering neural systems, that is actually implanting systems, or as Geshe Lakhdar mentioned yesterday, wearable technologies. So how can these wearable technologies and implantable technologies help people with neurological disease, mainly movement problems? That's mainly what we're interested in at the center in Seattle and our other partners. Other examples showing the promise of neurotechnology are shown in this figure. And these are just a few examples from laboratories around the world. In the upper left, you see a young girl wearing a hearing aid. Cochlear implants are fairly common to help people that can't hear. There's some, and we'll discuss this in a little while, there's some controversy about using cochlear implants, and we might hear a little bit from our next speaker about neurodiversity and some of the challenges and opportunities that are involved. In the middle, you see a woman with a robotic arm. So someone who has lost a limb. Can we build new parts and have those controlled by the brain? Can we replace body parts? In the upper right, you see another device that's implanted, and it controls from the brain residual muscle. And movement of that residual muscle then controls a movement of the arm. Below that figure, you see someone who's wearing an implant that records neurons directly from the brain. This is a patient that was completely paralyzed, I believe, from a knife that actually cut his spinal cord in the upper part of his spinal cord. The woman with those sunglasses is an example that Nishan mentioned yesterday, a very similar example. He presented a device which had a camera, if you remember, which then went to mechanical stimulators on a person's back. This device that you see the woman wearing the glasses, this is a device that turns light into tactile stimulation of the tongue. And the geishis all remember the experiment that we did last week about when we mapped the brain, and they all, I think, know why the tongue would be better than the back for such stimulation. Remember? Because the density of receptors in our tongue and our face is much higher than on our back. And we did that experiment to suggest why this is a better method than perhaps that method of stimulating the back, right? And finally, the one in the middle, the circular one with the grid of electrodes, that's actually a retinal implant. That's an implant that is inserted into the back of the eye, which is then connected to the optic nerve, which can then help people who are completely blind see shapes. It won't allow fine detail, but for someone who's completely blind to be able to perhaps navigate a room is a tremendous advance. So that's a couple more examples of the promises that are currently coming out of research labs. And the purpose of these types of technologies are at multiple levels. They can help retrain people who have had injuries and are recovering. It can help augment people with disabilities, for example, with artificial limbs or lack of muscle tone, and also perhaps remote assistance. Perhaps if we can connect the brain to machines, we can actually help people by assisting them in their daily life. So there's a large promise and possibilities for technology. Some more invasive technologies that are currently being investigated are transcranial magnetic stimulation. So by stimulating the brain using magnets, focused stimulation, we might be able to activate certain parts of the brain and perhaps even target deeper parts of the brain by focusing that magnetic stimulation. For a disease like Parkinson's disease, one promising technique is implanting electrodes into deep structures and then having something like a pacemaker. You've probably all heard of pacemakers for people with heart problems, but these are pacemakers essentially for the brain to help people with movement problems. And some people who have had these implants consider it to be a miracle, that someone with Parkinson's disease has shaking. Once that switch is turned on, the person's shaking goes completely away, and they can then drink water and move around with almost no problems. So these are just a few of the fascinating advances that are coming out of science. Now, some more controversial, perhaps, research. This is research that was just published a few months ago. And what researchers, this is research coming from Austria, what these researchers did is they took embryonic stem cells and they grew these stem cells in a dish. And in the proper environment, these stem cells actually became what they call a mini brain. And these cells actually developed a little bit of cerebral cortex. They developed some ventricles. They even developed a rudimentary retina. And this is all grown in a dish. These cells even showed some electrical response. Is this tissue in a dish conscious? The investigators say that, well, it didn't have the proper nutrients, the circulatory system wasn't complete, but it actually showed development of the similar structures that we have. And they said it wasn't conscious. I'm not sure that they're correct. I'm not sure how they know that this tissue in this dish is not conscious. So how do we respond to something like that? They created this quote-unquote mini brain to investigate brain development and perhaps neurodevelopmental problems. But what do you do when the experiment's over? And I think those are questions that are not answered. But perhaps maybe less controversial are some things that you may have heard of. And this is an example of something that's done very commonly. This is a cochlear implant. And this is an example of a little baby who's never heard before. And he was implanted with a cochlear implant. And what you'll see in this video here is the first time that this cochlear implant is turned on.
Here we go, it's coming back on, and he's back on again. See how he turns?
Turn. Hi, Jonathan.
Stop the sucking.
Hi.
Good.
Could
That's
you
real good.
hear that? Hi, sweetie. Could you hear that? Hi. Hi.
You got that, Dad, right?
Hi, Jonathan.
Look at that.
Hi.
That's so sweet.
We call that a late Christmas present.
Hi. Good job, buddy.
That's really good.
So that's an illustration of one neurotechnological advance that has made it into medicine and is fairly common. Another example, as I mentioned in one of the figures, is a retinal implant. And so what you'll see on this example is a man who's blind, and he has an implant, and he's trying to use this to see for the first time. So this is a man who's blind.
I saw something on the left. I mean, it was something round on the left. I only see two objects.
That's okay.
There's
Only
a-
two. There are only two.
Okay, and so it's round on the left, you know, and then the one on the right, it looks like it's longer, and it's curving like a little bit like this way.
Yeah. So it's okay.
It must be a banana. I mean, that's what it looks like.
And the left, what do you think is the left?
It's round, so, you know, apple. You know,
You can touch it.
that's
You
the
can touch it. Yeah.
okay. Now when I just estimate a little bit exactly, but the very center of the shape that I keep seeing is right here.
Yeah.
And two more examples, and I don't think I'll show the entire video of these two because they're a little bit long. But these two videos are from two separate laboratories showing a brain implant recording from nerve cells in motor cortex. And these are two patients from two separate labs, which are one woman had a brainstem stroke and is completely paralyzed from the neck down. The other woman has a spinocerebellar degeneration. She's also completely paralyzed from the neck down. And as you'll see, they're using brain activity, essentially thought, which is then converted into electrical signals to control a robotic arm.
That worked.
Oh, I wasn't paying attention.
Drop it. There we go.
That was a complete one.
Not a big bite.
Yeah, just took a little taller.
One small,
Doesn't
one small nibble for a woman. One giant bite for DCI.
So BCI stands for a brain-controlled interface. Just one more quick example from a different lab showing a very similar technology. And as you can see, she has that a block on her head. Through that block, there are many, many electrodes implanted in the motor cortex, and you might be thinking, well, if she can't move, how is she controlling that? What she's doing is she's imagining a movement, and that imagined movement is then controlling that arm. And after a series of training, the computer learns that particular signals mean something, and the patient also learns better how to control the device. And with more and more training, the computer learns better, and the patient also learns better. And these are patients that have volunteered for the study. No one forced them to participate. I've seen interviews with these women, and they say that they believe that what can be done with them and this early work is something that they are contributing back to society, and that they feel that this is something that they're almost obligated to do because they can. But much of this research brings up questions about how we should act and what can be done with this information, what should be done with this information. And I want to go through some of these potential problems that arise from this new research. And I'd like you to think for yourself, how might you respond? What is the right thing? What is the moral and ethical way to respond to this research? And it spans a number of different topics and realms, I think. And one is, what are the legal issues involved with this? If you had a technology that could tell if someone was lying, for example. I mean, you may have heard of polygraphs, but what if there was a brain scan that could tell whether someone was telling the truth or not? Would that be a good thing to use in a court? Would it have to be 100% safe and reliable? Or would you be satisfied if 99.9% of the time that brain scan would be truthful? Would that be okay as evidence in a court of law? How should these devices be used to measure life and death? How should these technologies be used to indicate whether someone is mentally competent or not? What kind of legal status and what kind of legal evidence should these new technologies have? And who should have access to these data? Perhaps before you get a job, your employer might say, please step into the brain scanner, and we're going to ask you some questions about your behavior. Would that be a good thing to do? Maybe that would prevent people who are not, who may be lying on their job application. Would that be a good thing to do? Should employers have access to brain data? There are two companies that are currently in existence who would like to bring a brain scanner near you. Sometimes you may have seen those photo booths, and you might go into a photo booth with someone and you get that strip of photographs, you're making funny faces or something like that. Well, what would happen if instead of that photo booth, you can go in and you can get an MRI scan of yourself? And you might be walking down the street and see one of these little booths, and maybe with your boyfriend or your girlfriend or a friend, and you'd like to know where they were the night before. Wouldn't it be nice to have one of these little scanners that you say, hey, step into the brain scanner, and I'd like to ask you some questions. These two companies would actually like to do that, and they'd like to commercialize this type of technology. And this is directly from their website, where they would like to actually bring a brain scanner to the public. Is this a good thing to do? Or does this open up some problems about who should have access to this information? The other question is, if we have these technologies and we try to cure people, is that the right thing to do? Or is it the wrong thing to do? Should differences in people be celebrated? Do differences in society actually make us more human? And this is a photograph from this past summer in Seattle. And on this is a public bus. There's an advertisement for Seattle Children's Hospital. And on this bus, it says, let's wipe out cancer, diabetes, autism in his lifetime. And you might think to yourself, well, that would be a good thing. It would be nice not to have cancer. It would be nice to get rid of diabetes. It would be nice to get rid of autism, right? We would all probably think that, and that's what Seattle Children's Hospital thought. But some people were not very happy with this ad at all. There's people in the autism community that were very upset with this ad. They said, we don't have a disease. We're just different. You have the problem. We don't have a problem. You have a problem. We're perfectly fine the way we are. It's you with the problem. You have a problem dealing with us. And so should these differences, this neurodiversity, be celebrated? And someone who has different abilities, maybe that makes us more human by helping them, by working with them, by getting their different perspective. So maybe we shouldn't be trying to cure people. Maybe we should just be trying to get along with people. So perhaps we need to think about what's normal and what are the benefits of having people that are different than ourselves. One of the questions that I posed to the geishis last week was, if you had a pill that could make you smarter, would you take it? And the first question that they responded back to me was, well, what are the side effects? And I said, well, that's a good question. And you can play with this question a little bit more. But if there was such a pill and you took it, would it be cheating? If you had your exams, your students at the side here, if you were going to have an exam and you could take a pill that would increase your score by 10 points, 20 points, 100%, would you take that pill? Or would that be considered cheating? We can't do that in the Olympic Games, right? For athletic competitions, you can't take all kinds of drugs. But could you take a drug to make you smarter? And there's research going on to see that maybe something like that might happen. We certainly have drugs to help people with cognitive deficits like Alzheimer's disease. But what does it mean to perhaps enhance somebody who's already normal? Is there a difference between that and helping someone who perhaps has a deficit? Other things that we need to think about is, this is an example in the United States where there's some discussion that the government is using brain scans to perhaps extract information from people who may not be willing to actually give it. Is this a good thing or a bad thing? If someone perhaps was going to do something very bad, and you can put them in a brain scan, and whether they volunteered that information or not, you might be able to gain some information. Is that a good thing? Or are a person's private thoughts private? And no matter how you get, and you should not be able to gather that information unless somebody willingly gives it to you. Is that a good thing or a bad thing? Maybe it depends on exactly what kind of information that is. Perhaps that information would save millions of lives. Does the means justify the ends? Another question that comes up with these new neurotechnologies is identity. And that is, sometimes when something would be worn or implanted, it actually becomes part of the person. And an example would be, you might recognize Stephen Hawking in this picture, who has ALS, a neurodegenerative disorder. And you may have seen him on a video, and he has that very mechanical, robotic voice. And there are many better voice synthesizers, but he has selected that he'll keep that voice because that voice has become part of him. He doesn't want to change him. And so it's not a problem with him, rather it's a problem about how we respond to him. So when does a device become part of a person? Another question is responsibility, and that is, when you implant these devices or you wear these devices, well, what happens if they fail? I mean, none of these mechanical devices, electronic devices, are without failure. I mean, we have power outages here. What happens if the power to an electrical device fails? And what if that device then hurts someone? Who's responsible for it? Is it the person who implanted the device? Is it the person wearing the device? Is it the device itself? Who's responsible for what happens if they fail? And how much autonomy, how much control do you give to the device versus the person? And I don't know how many of you have seen this Spider-Man movie, but this Spider-Man movie this is the evil villain who has a robotic device implanted into his nervous system, and part of the device is automated, and he controls part of the device. How much device do you actually give? How much control do you give to the device versus how much do you give to the person? And these issues having to do with neurotechnology are reaching society at this point. And this graph, this picture shows a couple examples of cases that have reached the top court in the United States, the Supreme Court of the United States. They've made a couple rulings partially based on brain imaging that have shown that young brains are not completely developed. And they've used these data to show that the juvenile brain, someone about under 18 years old, is not completely developed. And so in the United States, in many states, adults who are accused of various crimes can actually be put to death. But the Supreme Court ruled that based on data about brain development, that because younger brains are not completely developed, we cannot put those people to death. So whether you believe in the death penalty or not, the U.S. Supreme Court has said that you cannot put young people to death for their crimes or put them in jail for the rest of their life. Part of it based on brain imaging data. Other issues to think about are what are the benefits and risks of these? Is there a difference between repairing damaged nervous system versus enhancing normality? And when does a person end? And another question is, what about the security of these signals? You saw an example of a device that signals might be sent wirelessly, or information from the brain will be sent to a recorder. Well, what if somebody could intercept those signals? So not only get those signals, but what about put signals into the brain without a person knowing? That would probably be a bad thing, but how do we protect against that? Other issues are safety. This is the device right now that you can buy on the internet. And this is a transcranial stimulator, which you wear on your head, and it actually sends current directly into your brain. And it's sold not as a medical device, and that's how they get around some regulations. But they say it's safe, but is it really safe? What's the long-term consequences of sending electrical current into your brain? They are selling this particular system, which I haven't given you the name, to help people who play video games, to sort of overclock their brain and to make them better video game players. But the safety of these is really not quite understood. And finally, justice. And that is, what responsibilities do we have as society? What responsibility do we have as researchers and scientists about what happens to these technologies? Geshe Lakhdar mentioned yesterday, we talked a bit about the atomic bomb. Scientists who worked on this couldn't see, or maybe they did see, some of the horrors that would result from this new technology. What about this neurotechnology? What are some of the possible future consequences of developing this? Some of us as researchers, we don't have control once we tell others about what we're doing. We don't have control about what they do with our results. And so what is our responsibility when we make this? And who should make the decisions? I think that it's a decision that needs to be made by all of us. It needs to be made by the end users, the patients. It needs to be made by our students and our young people, because they're the future. They need to have a voice. It's not just the scientists. It's not just philosophers. It's every segment of society that will be affected by these new technologies. And so I think it's a conversation that all of us should have. And as I always say, there are no bad questions, except that one kind. And that bad question is the question that's not asked. So thank you very much, and I hope that this has stimulated some interest in you.
wanza tushen pobe memambu shuchi tandan zambilin di wanza tushen pobe memambu shuchi chagores ani labarda arino ne tandabe wanza tushen pobe memambu chiche antegale tandan doson de la dola ni apache tembun den doson tangu yoresune kalu tusnan tisonza ani 단다보든 천리바성 용무부 돌아 시부지 제바 시역이orde 완자 투션 법이 단다디 완자 투션게디 나서 멤버든 지지 용돼야디 아니 중국 간이지 용구여메게 아니디 제바 시역이orde 저지다 계세들 제바 시비여나 천리비토는 들 아니 고야게 탈란다보디 간지지 좀야게 체지요레스는 어떠시 저티니
So in your presentation you talk about the neurological disorders and the range of its effect on a population, and in US alone, the cost of treating and taking care of these neurological people with neurological problems is like billions of dollars. So even though we came to know about these problems, do you have research done why these kind of neurological disorders are there? Why they are coming why they are having more and more people with this kind of disease.
Yeah, that's a very good question. There's a few reasons. One may be better diagnosis. So physicians and caretakers are recognizing these disorders and classifying them in different ways that allow us to count and monitor these disorders. Another factor could be lifestyle changes. Diet changes could be resulting and exercise changes could be resulting in just general poorer health. Certainly obesity is an issue that's correlated to some of these problems. Another factor is just our aging population. So our population as a whole is getting older. So there are more old people. So there's more Alzheimer's disease, there are more strokes, and so there are more elderly. So I think those three factors can contribute to these higher numbers that we're seeing.
단대 그 차랑 아주 기적다 레베기 나자 단제베기 아니 네베기 릭디 아니 장가 마르마 용구요레스티 용구야기 아니 금젠디 아니 네주숨 투요르삼 그두스 당보디 카레슬라미 베나직 등산 아니 직 멤버스기 아니 직 나자 ngocho야기 투제든조 아니 세 토르 레비 용두 잠발라 아니 ngar 나자디 콩돌라 마징이기 아니 직가다 나자든조 ngocho야 기 니발레 용두 잠발라 네바든조 아니 마운 용구요레스 그가나시 니와디 카레슬라빈베나 아니 직당 안조기 직 미제제나디 아니 교와두요레스 베차샤베나 아니 루제 메와다 티가나시 엔지가 칼라 사단 든조 아니 교와두 용두 잠발라 베차샤나 따딩자 루제 메와다 아니 지가 칼라 망부직 아니다 놈다 딘디 젠지 제단다 아니 갸그네스 시나이도 샤갸 타이크 나자 제자다 딘데 나 용두 잠발라 딘조기 아니 지게야 딜라 쫀지 요레스 제자 나자 딘디 키 용구 요레스 티가나 신치 카레슬라빈베나 아니 팅산다 지가 메다 든조 야르게 침백 좀즈는 때네 미기 체제데 링루친 요레스 미기 체 링루친 비 좀즈는 때네 아니 간주기 지조 나로라 겐고마 요레 겐고마 요두 잠발라 고 게베기 좀즈는 때네 로 게드야다 데베기 아니 나직 리페샤잖아요 템바냠드야다 딘데기 엔 나제리 망부 용고 요 송자 창념고 토네 지조 나로라 아니 지가 원제기 교육이 네베그릭 장가망두 요레스
네 도말 아니 경험은 뭐 상물이야 아니 저희들이 쉬어다 접직 아니 단다 공기 다 집앞에서나 가르스나 레버드레스는 비무스 망고치 손스 레버디 다지제 갑대야 투리 때문에 제고 그래마다 심어 패지 마시버기 때문에 송송 디송인데 투리기 아니 레베기 덴밤디 투리기 덴밤디 아니 수지게나 코랑기 송인디기 지여베 원나마도 시엔지 제고 그래 주티
So you talk about a lot of problems with neurological disorders and interactions between brain and the machines. And it seems that machine is the kind of authority that controls this kind of, I think, people with neurological disorders. So who is the one who is actually controlling the machine itself?
That's another good question. And I think it depends on how the machine is built. And some of the control can be given to the person who can imagine an action, which is then translated into a signal to the machine. But then the machine can also have some control. So for example, a person can initiate the movement of an arm, but once the arm gets near a particular device or item, the machine can take over and continue the response. One other factor that I think is important to note too in the future is feedback to the person. And that gets to the question of how much the machine influences the result. And what I mean by that is that perhaps if someone is moving an arm and the arm gets to a cup, for example, that machine will then send feedback to the person's brain, which will tell how much force is actually on the cup. And so it's actually an interaction between the machine and the person that will actually make the best machine-brain interface.
Tanda ani wangzi ki ani mala ani kyun shorji ani dila tanda ani tuji dindu zuche ani ta roba chi de ki dinzu ki nanglo la ani tangzi chingin ki wangzi yu dingi de suris la yung du zambala ani mi ger neba ger korang da tegana shi ani tuji di ningala ani wangzi yu de chek yores tangbung la ani tuji dinzu ani 장금 기 애니 겨와 강야 롱원지를 그 용도 잠발라 데 통말 기 애니 근게 기 근원 칭에 디 미디 기 애니 삼로당 요라고 삼로당치 지두 잠발라 아니 그기 당에 디 애니 미디 차디 요레스 원세니 임베나 아니 그 펠라다 포워드 딘데 지킨 담라 레스 차베 기 젤라 아니 데네 아니 디 담루 주다 아니 지가 카르치 마지세디 야 원세 칼라 칸섬지 아니 주제 딜 요레스 제자단 주제 디기 아니 지 포워드 세밍도 잠발라 tangan tujik lakwa do shimbina di sim yung sambala kugi ani simdang khande simgu yeme simba di ani thamhe khande do mindu ki neju di ani ya level ya tang yores ya level ya tang yung sambala tadi tham thana tham thai do le thana le thai do dik do mindu ani dine tuji dine ya yung we ki ani da dela pa we ki ya lebe ki samlu tang tang an juwa tang yung yores cheza di yung sambala ta dini ni pa leba da ani tuji ni par ki delam di ta 파조 아니 찍 파조 다당레 집에 그 돈이 아니 다 내가 약속이 제 두고요레스